In this session we'll do an example of uniform distributed load. This is the uniform distributed load, simply supported beam, and the uniform load is 3 kip per foot. So first of all, again, we need to calculate the reactions. So to calculate the reactions, we'll take moment about either B or A, and let's say we're taking moments about point B. So we'll do is sum of all moments about point B is equal to 0. Here we need to understand the concept, and this concept is for the uniform distributed load. I say this is a piece of uniform distributed load. This means 3 kip per foot means there's 3 kip for each 1 foot. 3 kip, as if it is 3 kips for each 1 foot. So to solve this, normally what we do is we replace the entire thing here by an equivalent value, which will be something like this. I'll call it uppercase W, and this is equal to omega or lowercase w multiplied by L. This will be the value of the force. So this force will replace this uniform load in the calculation. So I just want this to be clear as we go. So for this part, we'll have, if we take moments about point B, this R reaction at R will rotate in this direction, which is negative clockwise, and for this entire thing it will be replaced by an equivalent value of force sitting in the middle. This will be always the case. So the rules for the uniform load, it will be replaced by uppercase W, which is the force, is equal to lowercase w multiplied by L, and it will always be at a distance of in the middle. So whatever this distance is, and this is an important concept to understand because this will apply to the entire calculation also. So this will be always L by 2. So let's go ahead and calculate this. So of course this will rotate. So this is imaginary. This will rotate in this direction, of course. So this is positive. So we have 2 points. We have plus minus RAY multiplied by the entire distance, which is from here to here, and this is equal to 32 feet multiplied by 32 feet. Then we have plus, and the plus will have 2 parts to it. We'll have first of all the force, which is uppercase W. So W multiplied by the distance. This distance is L by 2. So let me just translate this because we need to. So this is minus again RAY multiplied by 32 feet plus. Now this part is the force part, and this part is the distance. Like this one, this is the force and this is the distance. So the force part will be omega multiplied by L divided by 2 is equal to. So if we do the numbers now, RAY multiplied by 32 plus W is equal to, again I want you to watch the units, 3 kip per foot multiplied by the entire distance is 32 feet multiplied by 32 feet divided by 2 is equal to. So you see here this foot and this foot will be cancelled out, so you'll be left with kip foot. So now minus RAY multiplied by 32 is equal to, plus this force will be equal to If you multiply 3 by 32 will be 96. 96 kip multiplied by the distance, which is equal to half of 32, which is 16 feet, is equal. So you see again, if you would like to, this will be in kip and this will be in feet. Kip and feet. So you have to understand this concept. So now if you isolate RAY is equal to 1536 divided by 32 and is equal to 48 kips. That is the value for the reaction. Now we'll continue with the same way that we used to calculate our reaction. So we'll do sum of all forces in y direction is equal to 0. And this will be, we have this force is upwards, this is downwards, and this is upwards. So we have plus RAY minus, we said the force is uppercase W, and plus RBY is equal to 0. So RAY is, we calculated this to be 48 kips minus the lower uppercase W is equal to lowercase w, which is 3 kips per foot multiplied by 32 feet, plus RB is unknown, is equal to 0. So you see again, if you would like to see the cancellation of units, this and this will be cancelled out, foot and foot will be cancelled out. Then we get RBY is equal to 48 kips, and this is because this is uniform load, so this must be equal to this. So that's for the reaction part. And again, like I said, the reaction part has this important concept that we need to pay attention. So now that we have done the reactions, there are 48 each, we'll move on to work on the shear force diagram. So for shear force diagram, this is not like the point load. In the case of point load, it was straightforward, you didn't need any calculation, but in this case we'll need calculation, and this is 3 kip per foot. And like we said, this uniform load is as if it is 3 kips at each point. So imagine if we, in the case of, we have the first reaction is equal to 48 kips, and this is equal to 48 kips. So let's see, if we go with this part as 48 units, or 48 millimeters, say for example, say this is equal to 48 millimeters. Once you move 1 foot here, this will bring it down by 3 kips. The second 3 kips, 3 kips, 3 kips. So you see this will keep on doing 3 kips until it goes here. This is why we need to calculate the values of shear at these suggested distances, and I suggested distance 8, distance 16, 24, 32. So let's do that. So also we'll do the same as we did in the case of bending. So I'll say shear from left, distance of 8 feet is equal to how much? So again, you see, if we do the sketch for that part, you have this part is reaction, this is, and this is distance is 8. So we have this part is going up and this part is going down. So we have plus 48 minus, now the W here is equal to omega multiplied by L is equal to, so plus 48 minus omega is 3 kip per foot, and L in this case is 8 feet, and that is equal to 24 kips positive. So if we do shear at distance of 16 feet is equal to how much? We'll have again plus 48. Again, if we do the sketch, is very similar to this one. This is 48 and this is 3 kip per foot, and this distance is 16. So we need to do it plus minus. Now the W is changing because this is why we are doing the calculation. The distance, as the distance changes, the shear force also changes. So we have 3 kip per foot multiplied by 16 feet is equal to 0. Now if we do shear force from left at a distance of 24 feet is equal to how much? The sketch is the same, so it will be again plus 48 minus W is 3 kip per foot multiplied by 24 feet is equal to minus 24 kips, and watch the unit is kips, is not, there's no feet in it. And if we do at a distance of 32 feet is equal to how much? This should be equal to the value of 48, because 48 had to bring this diagram back to the 0 point. So is equal to how much? So it will be again 48 minus 3 kip per foot multiplied by 32 feet, and this is equal to minus 48 kips. Now if we would like to sketch again, we just put the points. So we have, this is 1 point, and this is the second point, third point, fourth point, and the fifth point. Now how do we connect these? Are they straight line or curve? And again we go back to our calculus skills. So if you look at the equations here, this is 48 minus W is 3, and this is X. And again 48 WX, it's 48 WX, 48 WX. So the equation is simply a linear equation which has only, so it is, the equation is 48 minus W is 3 and this is X. So this is the equation. This equation is a linear equation, and for a linear equation we sketch this as a line. So it'll be like that. That will be the, and of course this has to close here. Then this will be our diagram. This is the shear force diagram. Now if we would like to do the bending now diagram, so for bending diagram, these values are 48 kips, and this is equal to 48 kips. Now with the bending, we'll do same thing. We'll go to 8 and 16 and 24 and 32. You might ask us why 8 and 16? Change them, make them here, because you are sketching a diagram. So that choice is yours. This is my choice. So we'll start with, say, bending moment, or sorry, just moment from left at a distance of 8 feet is equal to how much? Of course, we know that the bending moment at this point is equal to 0 because there is no distance, and from the definition of bending moment, it is force multiplied by distance. Because there is no distance, so the bending moment is equal to 0. So again, we'll sketch this as we go. This is the point that I would like to calculate the moment here. So this is equal to 48, and we said we'll replace the uniform load. We'll replace this uniform load by an equivalent or resultant of something in the middle, which we'll call as uppercase W, and this will be a distance of half of the length. So in this case this was 8, so this will be 4 feet. So if you look at the rotation, this will rotate in this direction and this will rotate in this direction. So this is negative, this is positive. So if we do the bending moment at this distance, it will be equal to minus 48 multiplied by 8 feet plus the W multiplied by 4 feet, or let's call it L by 2 is equal to, so this will be minus 384 plus the W is equal to WL multiplied by L by 2 is equal to, and this is minus 384 plus W is 3 kip per foot multiplied by 8 feet multiplied by 8 feet divided by 2 is equal to. And again, I will emphasize on this because this will help you understand. This is the force and this is the distance. This is the force and this is the distance. So this is distance, this is force. Of course, this is force and this is distance. So this will become is equal to minus 288 at the skip foot. This is the first value. So I move to the next point, which is a distance of 16. Let's do the sketch. The sketch is same, but just to help you understand. So this is, again, this distance is 16 feet, and we're taking this point here. This is 48, and we say the equivalent of this uniform load will be somewhere here in the middle, and we call this uppercase W. And the distance is L by 2. So rotation, this will be same here. This will be in this direction, negative, and this is positive. So if we do moment, a distance of 16 feet is equal to how much? The equation is same. So it's minus minus 48 multiplied by 16, the distance change 16, plus WL multiplied by L by 2. I'll keep writing this to be able to show you how we derive this, if it is curve or line. So minus 48 multiplied by 16 plus W is equal to 3 kip per foot multiplied by 16 feet multiplied by 16 feet divided by 2 is equal to, and this is equal to minus 384 kip foot. Now if we want to do the distance of $24 is equal to how much? So the sketch will be the same, so I'm not gonna just do the sketch again. So it will be equal to minus 48 kip multiplied by 24 feet, then plus WL multiplied by L divided by 2 is equal to, so 48 multiplied by 24 48 multiplied by 24, that is minus, plus we have 3 kip per foot multiplied by 24 feet multiplied by 24 feet divided by 2 is equal to minus 288, that is kip foot. Okay, so now we have one more point to go to, and that is the 32. So let's do the 32 also here. So I'll say bending moment from left at 32 feet is equal to how much? Now, as we have said, this should be equal to 0, so we'll apply the very same equation, and if it comes as 0, it means that our calculation is correct, so it will be the same. Again, if you will, it will be and then the uniform load, and we're taking this at this point, and we have this will be the equivalent in the middle, W, this is 48, and of course this will rotate in this direction, which is negative, and this will rotate in this direction, which is positive. So same, be minus 48 kip multiplied by 32 feet plus WL multiplied by L by 2. And this WL is the uppercase W, is equal to, so minus 48 kip by 32 feet plus we have 3 kip per foot multiplied by 32 feet multiplied by 32 feet divided by 2, and if you calculate this, this will be 0. So now I have all the points, I calculate all the points, and if you go back, see this is like I suggested before, we are using, I'll go to to the other diagram. I think all the values here. The only thing I have to add is in here is the bending moment from left at 32 is equal to 0. So that I'll have all the points here. This one and this one and this one and this one. So I have all the values. So the first value here is minus 288. The second value is minus 384, and the third value is minus 288, and this is equal to 0. So now how to join these points. Back to the same concept that we talked about, and if you look at all these equations, you will see here, you see this is constant, this is x, this is constant, and this is x. So if you go back to the equation to create an equation to see if this is linear or not non-linear, you will see it is equal to, take this 48 is 48 fixed here, and this 8 is, and this 16 and this 24, these are the x's, 48x. This is of course minus plus. If you look at here, this is w, which is fixed, which is a 3 kip per foot, 3 kip per foot, and it is 3 kip per foot. What comes after that is this L, and this is L, and this is LL and LL. So it means it is 3L square divided by 2. So this becomes minus 48x, and L of course is x. L is x. So this is x. So 48x plus 3 divided by 2 is 1.5x squared. So you see this equation is not a linear equation. So that's why when we connect these lines, it becomes like that. This is why this diagram is like so.